Never actually heard that read out loud before. That's just like the buyer using websites. And now I really need to change it because I'm so freaking mortified. Anyway, yes. Hey, everyone. I'm Aaron Bassett. So I've been a Python developer for a very, very long time. I regard myself really as solely a Python developer for much of that time. I've given a lot of talks at Python conferences, including right here in this room in 2018. I'd heard a lot of good things about Rust. Other Python developers have made the move. They told me about like how it was not as buggy, how there was better developer tooling, how there was like C and package management. But I'd been in Python for a while, and I've kind of solved all of those issues for myself already. You know, I had a process that I was familiar with and that worked for me, and I didn't see those as issues anymore. Like, that was all solved problems. Fast forward to recently, where I got approached by a Web3 company. Now, I'll be honest, I was a little bit skeptical at first about joining a Web3 company. As I'm sure a lot of you are when you hear the words Web3 and blockchain. Now, this isn't going to be a talk about blockchain. I'm not going to get into what changed my mind and why I decided to go work for that company. It's enough to say that I did some research into tech, was really impressed, and decided to move there. Now, I wasn't overly concerned by the fact that everything they built was in Rust, even though I didn't know Rust, because I'm a DevRel. Okay, I'm not a core engineer. You know, most of what my job is working with customers and getting them used to using our products and educating them. And it's like demos and example apps and working with SDKs. And everybody everywhere has a Python SDK. I wasn't concerned about that at all. I had in the back of my mind somewhere that I probably would have to learn Rust eventually. But every time I'd sit down to look at some of our codes, well, it looked foreign and unintelligible. And honestly, I was a little bit intimidated. So I'd go and find something else to do. You know, it had been a very long time since I'd read code that I'd struggled to comprehend. I wasn't used to feeling lost anymore. So I would go and find something else, something I knew, something that was safe. And we're going to look at some examples of code from our SDK, and you can tell me truthfully if you wouldn't have done the same. So I'm going to read exactly what this is here. So these are all code examples from a single module in our code base called Grandpa. And Grandpa stands for Ghost-Based Recursive Ancestor Deriving Prefix Agreement. So what does a ghost-based recursive ancestor deriving prefix agreement module do? Well, it allows a set of nodes to come to BFT agreement on what is a canonical chain. Okay, I'm lost and I've not even looked at the code yet. Now I'm going to attempt, to the best of my memory, to walk through these examples the same way I did when I was first thinking about learning Rust. We'll start off slow with one of the least complex examples. Okay, so looking at this code, I can probably guess that pubfn means it's a public function. It takes an argument called call. I know enough by typing to guess that our call argument's type is a call object of some sort. No idea what the % is about, or the T in brackets. Looks like our function is going to return a result, more angle brackets. Maybe this means that the result of the function is going to be either a tuple or some sort of error. Then we have an if let. I'm assuming let is for creating variables. Not sure why the if is there. Where did this equivocation proof and key owner proof come from? Are the curly some kind of spread operator? Does call expand into those? Next example. Awesome. More angle brackets, love those. So I'm guessing IMPL is for implement. Not sure why it has angle brackets. Does implement take an argument T of type config? Is it implementing T? Is palette an argument? Why are there more angle brackets after palette, but with no config this time? Is it the same T that we were seeing in the previous one? And why does some lines have semicolons while other lines don't, and some have semicolons and question marks? I'm starting to get really pretty lost at this point. The last example, and I'm just nope, I am out. This is just incomprehensible, makes no sense at all. And that's basically a speed run of my first few months looking at that code base of the company. You know, I remember more than one occasion distinctly shouting at my monitor because I couldn't figure out where the fuck do those variables come from. They're not defined anywhere. They're not imported. You just suddenly appear. Why is everything in angle brackets? It just didn't fit into any mental model that I had. So how did I go from being terrified of Rust to kind of loving it? Well, I had a baby. And remember when I said that I wasn't worried about learning Rust because I was DevRel and not like a core engineer? Well, it turns out when your product is a Rust framework for building blockchains, and all of your peers from like the CEO all the way down are Rust developers, and all of your users are Rust developers, and you want to like help your users and be a good asset to your colleagues and be successful in your job so you can keep your job, well, then you need to become a Rust developer too. I like my job, but I really like being able to provide for my kid. Like keeping your child clothed and fed, it is an incredible motivator. Like really helps you put aside your years and prioritize. But I had to stop trying to learn Rust by reading Substrate's codebase. I'll admit, it was humbling, but I needed to go right back to basics. What's chapter 1, page 1 of every programming language book out there? Setting up your development environment. So that's where I started. Now, I am very particular about my Python environment. I often need to have multiple versions of Python running side by side, so I use pym to manage them. Every project gets its own virtual environment, and I never install anything globally. A typical workflow for me is like a pym install whatever version number I need, and pym virtual env version number, start working. Rust up. Rust up install will install the specified version of Rust, or you can do Rust up install stable, Rust up install beta, Rust up install nightly, and it'll give you like the most recent version of each of those channels. Rust up toolchain default, like pym's global will set like a default version of Rust for your environments, or you can use Rust up override set, which will override your default version of Rust for a particular directory. So very similar workflow. Like this is very close to what I already had set up for Python. Really, really good start. As you probably inferred earlier, I'm also pretty particular about dependency management. I did a whole talk about it back at PyCon UK in 2016, and honestly, not much has changed since then. The main points of the talk was that you should never use pip freeze. Instead, you should add your dependencies to a spec file and then use pip tools to generate out your requirements.txt, which acts a bit like a lock file. Rust has cargo. Your dependencies go in a cargo.toml file, and cargo generates your cargo.lock file for you. You can have dev dependencies, build dependencies, platform-specific dependencies. You can inherit dependencies. You can override dependencies. But to jump on a plane, Cargo vendor will download all your remote dependencies in your local directory and even print out like the necessary config changes for your project to start using those local dependencies. Dependency management is hard. Like I am not one to shit on like Python's dependency management. I know how hard those guys work. You know, I know they get a lot of like flack for it. It is a really, really hard problem. But Cargo's implementation is the best I've seen so far. Like it took me a long time to find a dependency management workflow I was happy with in Python. But with Cargo, so far, it just kind of works. My projects also tend to lean towards a modular architecture. I work for an edtech company where we white label our content and platform with different publishers around the world. It was all built in Django, and we tailor the platform to best fit the pedagogical standard, that's a fun word, of each country. These customizations made it too complex to have a single multi-tenant deployment of Django. Too many minor differences between things. There was still a lot of shared functionality, so instead we created individual packages for each shared piece of functionality, and each instance then was a pretty basic Django project, a little bit of boilerplate, and a really long requirements file. To make this modular architecture manageable, packages had to follow the same conventions and structure. They had to be easy to edit, publish, deploy. They had to also be well tested, and they had to be well documented. Mark Smith did a 2019 EuroPython talk called "Publish a Perfect Python Package on PyPI." Sorry. Try saying that 10 times fast. It does a great job explaining how to do all of this when creating a Python package. Spoiler: it's really, really complex. You should just use cookie cutter. In Rust, again, it's Cargo. Like Cargo new will create a new crate, Cargo test will test it, Cargo doc will build your docs, Cargo publish will package up your crate and publish it to the registry. And if it's a public crate, it will also deploy your docs to docs.rs for you automatically as well. Having a consistent coding style is vital in making your projects maintainable. So I worked at a company which is going to remain nameless, and you'll understand why in a second. My colleagues there were very smart people. We had an interesting product, loyal customers, ample investment. Company values were all about like transparency, equity, work-life balance. We had a 4-day working week, no crunch. Like, it should have been a dream place to work. I fucking hated it. I dreaded going to work every day. It was the worst place I have ever worked. The original version of the site was written in PHP. Okay, this is nothing slating PHP. Okay, it just was. That's a fact. I think maybe Drupal. It definitely wasn't designed to be a SaaS product, so they decided they were going to rewrite it in Python. That was field Python rewrite number 1. There was many. So they decided to rewrite in Python, and like most rewrites, it went way over time, way over budget. Eventually, like the BD folks were saying they couldn't wait any longer to list the feature requests from clients, and we had to start pushing out new features. So they decided they were going to stop the rewrite, take the parts that were written in Python, and kind of smush them together with the existing PHP site. So now developers are no longer working a rewrite, they can start working new features. But of course, development of these features is taking much longer than they thought it would because, well, things are error prone and things are like difficult, and developers are finding they're having to write the same code twice, once in PHP, once in Python. So they decided the only way to fix this problem was a rewrite. And not just rewrite of the remaining PHP scripts. No, this was going to be a rewrite of everything again. Because the original Python developers who started the first rewrite, well, they'd all burned out and left. And the new developers, well, they're looking at the code and, well, they don't see like the time constraints or the compromises or the feature creep or any of the other factors that influence the code. All they see is bad code. So they decided they're going to rewrite it all again, but properly this time. Yeah, they would repeat this pattern many, many times. I joined in the midst of rewrite number 4. I lasted 8 months, and I saw rewrite number 5 start during that time. Of course, the code base was riddled with technical debt, but you know what I hated most about it? The lack of any consistent coding style. Some code used tabs, some used spaces, sometimes it was 2 spaces, sometimes it was 4 spaces, unless it was a models.py file. They inexplicably used 3 spaces, just those files. Naming was also inconsistent. Some module names were pluralized, some were singular. Variable names would switch between snake and camel case, or if you were very unlucky and had to edit one of James's old files, he had a brief stint with Hungarian notation. The additional cognitive load of constantly adjusting to different coding styles was horrendous. After that experience, the first dependency I add to any Python project is black. First thing, black, installed, done. Second thing, Flake 8 and like 30 plugins. I lent everything from attribute order in my classes to like function naming. I have VS Code configured to display all linting errors and to format my code and save. I've also pre-commit hooks that ensure that any linting errors or formatting errors can't even get committed. I've become so accustomed to having these tools running that I no longer notice them, which is exactly how it should be. With Black's auto formatting and my editor flagging any linting problems, it is very rare that I have to fix anything before committing. I've become so reliant upon them that I'm way more likely to notice their absence than their presence. Which is probably why it took me so long to notice that my Rust code was also being linted and auto formatted. As well as Rust and Cargo, the Rust community maintains Rust Analyzer, which I installed in my IDE and then promptly forgotten all about. The fact that it worked seamlessly across all of my projects without any additional configuration floored me. It wasn't just a particular way that I constructed my Python development environment, which made the transition to Rust easier. It was also the way I've been writing my code, or more accurately, the libraries and packages that I've been using in most of my projects. There wasn't a particular moment in time when I decided that I was going to start using type hints throughout my Python code. Instead, it was more of like a gradual progression. A few years ago, I started working with the farm stack, which is like Fast API, React, and MongoDB. Fast API uses Pydantic for its data models, and Pydantic uses Python's type annotations at runtime for data validation. So I began adding type annotations to my code, simply out of necessity. I liked Fast API, and this is the recommended way to use it. At first, I only added the type annotations where strictly necessary, but I began to appreciate their benefits. Not only did it stop me from making silly mistakes, but I also became accustomed to the better autocomplete with my editor. Soon I was becoming annoyed when I would work with code that did not have type annotations. Eventually, I was annotating all my Python code, not just where required for Pydantic. Okay, so I think my development environment was pretty Pythonic, and it just so happened that it was also Rusty, Is that the term? Rustonic? Rustic? Rustful? I'm not sure. Anyway, I was pleasantly surprised to discover that the standard Rust development environment felt very familiar to the way I've been working in Python. But what were the high-level differences? Okay, most obvious, Rust is statically typed. And all types must be known at compile time. I thought this would require adding a lot of additional type annotations to my code. But actually, really, it didn't. The compiler can usually infer what type you want to use based on the value of the variable and how you're using it. I noticed no significant difference in the amount of annotations I needed to use in Rust compared to my Python. In Rust, variables are mutable by default. Not a huge change, but it did make me think more carefully about how each variable will be used, forced me to consider every time some data could possibly mutate. The first major difference took some time to click for me was ownership. This is probably the most unique feature of Rust. Ownership is a set of rules which governs how Rust manages memory. It enables Rust to make memory safety guarantees without the need for a garbage collector. Before Rust, all languages familiar with had automatic memory management and garbage collection. Memory allocation was never something I needed to consider. I know there's probably some folks in the audience who have never had to think about it either, so I'm going to do a quick primer on the stack and the heap. Both the stack and the heap are parts of memory available to your code to use at runtime. The stack stores values in the order it gets them and removes the values in the opposite order. Last in, first out. All data stored in the stack must have a known fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap. When you put that on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap just that's big enough, marks it as being in use, and returns a pointer. Because that pointer is a fixed known size, the pointer can go on the stack. Pushing the stack is faster than allocating the heap because the allocator never has to search for a place to store new data. It just gets added to the top. Accessing data in the heap is slower than accessing data in the stack because you have to follow a pointer to get there. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, cleaning up unused data on the heap, and all those other things are all addressed by ownership. I know this sounds complicated, but once you understand ownership, you'll need to think about the stack and heap very often. We've lost a lot of time here. There's 3 ownership rules in Rust. Each value in Rust is an owner. There can only be one owner at any time, and when the owner goes out of scope, the value will be dropped. So let's look at an example. A string is made up of 3 parts, which are stored in the stack. A pointer to the contents of the string on the heap, a length, and a capacity. When we assign S1 to S2, the string data on the stack is copied, meaning we take a copy of the pointer, the length, and the capacity. But we do not copy the data on the heap, what the pointer refers to. Okay, so we don't copy data in the heap. That means that both S1 and S2 are pointing at the same data, and that's breaking rule 2, which means that if S1 and S2 both go out of scope, then they'll both try and free the same memory. To prevent this, we assign S1 to S2. Rust no longer considers S1 as valid. This is referred to as a move. S1 was moved into S2. There's one type of data which doesn't move and instead copied, and that's any data which has a known size at compile time and is therefore stored completely on the stack. Things like integers and booleans. So how does ownership work with functions? It's pretty similar. Here's a rough example. At the start of our main function, S1 comes into scope. We then pass S1 into text ownership. Its value is moved, and S1 is no longer valid. The some string value of text ownership is not returned, so it goes out of scope and is dropped at the end of the text ownership function. S2 receives ownership of the value of some string from gives ownership function, and then on the next line, that value of S2 is moved into the takes and gives back function. Now, even though that takes and gives back function returns ownership of some string, the value was moved into the function and then moved back out again, which means that S2 is no longer valid. It lost ownership during those 2 moves. But in fact, by the end of the main function, only S3 is still valid. So at the end of that function, S3 is going to go out of scope, drop is going to be called, memory will be released. So you can see functions receive and return ownership, but needing function return ownership every time quickly becomes tedious, which is why Rust has references and borrowing. Okay, the ampersands in the code denote references. A reference refers to the data, but does not own it. And remember rule 3 of ownership, the value is only dropped when the owner goes out of scope. When functions have references of parameters instead of the actual values, we don't need to return the values to give back ownership, because the function never owns the value. We call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them, but when you're done, you have to give it back. You don't own it. Also, you can't modify what you've borrowed, at least not without getting the owner's permission. Like variables, references are immutable by default. If you want to give the borrower permission to change the value, then you need to use a mutable reference. So I have some last examples. We're going to try and run through them really quickly. This is a struct. You can define methods in structs. Methods must have a parameter named self of type self as the first parameter. Does this look like anything to some people? Recognize this? Very similar syntax. Rust also has enums. Enums are actually one of my favorite things of Rust, because enums give you a way of saying a value is one of a possible set of values, which is incredibly useful when combined with things like match the control flow. It also has a couple of built-in enums. One is option. Option encodes a very common scenario in which a value could be something or it could be nothing. This is actually incredibly useful. Another enum is result. Result variants are OK and error. Similar to option, OK variant indicates the operation is successful, and inside OK is successfully generated value. While the error variant means the operation failed, and error contains information about how or why it failed. So why are these my favorite parts of Rust? Like, couldn't you just kind of do it with some if statements? Well, match has an exhaustiveness requirement, which means that if you're matching on an enum, you must handle all possible variants. Add a new variant to an enum, but forget to update your match to handle it, you'll get a compiler error. Your code won't compile. Having a function return or accept an option ensures that you must at least consider that the value could possibly be none when writing code which interacts with an option. And if a function returns a result, but the caller does not handle the error, your application again will not compile. It does all these things to try and help you from shooting yourself in the foot. This doesn't mean that your Rust code needs to be horribly verbose. There is like a catch-all that you can use in match. You can supply defaults to option with like unwrap or and a bunch of other kind of like helper functions. And you don't even need to handle every error being returned as a result and where it's being raised. You can use propagate to let it bubble up and catch it higher up the stack. There's a lot more to Rust, more than I have time to cover here because we're at 25 minutes. But there's one last thing I want to talk about, and that is, what the fuck is T? Like, we saw it a bunch in the substrate example at the start, and more recently with like option and result, but what is it? So T is a generic and abstract stand-in for concrete type or other property. Take something like these two functions. They're almost identical. So let's swap out the concrete type with a generic. Now the function is generic over some type T. It has one parameter named list, which is a slice of values of the same type T, and it will return a reference value which is also the same type T. Die. For reasons this code won't compile, because Rust knows how to compare things like integers or characters, but T can be any type. So how, if you had like a country type, for example, like how would you judge what's the largest country? How do you decide, is it like by area, by population, by like GDPR, or no, sorry, GDPR is privacy, not like GDP, by exports. Like there's so many different things you could judge the largest country by. Like there's no way it would know how to judge every single type. This is where traits come in. I'm about to get my hand over here. But the compiler does tell us how we can solve some of these errors as well. It's saying here that we can restrict what types T can stand in for by specifying the type T must have the trait of standard, compare, partial ordering. A trait defines functionality a particular type has and can share with other types. The partial ordered trait can use methods related ordering, less than, greater than, and so on. The standard library implements this for like a bunch of different built-in types, integers, cars, etc. But you can also implement it for your own types as well. So if you decided that, okay, we want to order countries based upon population, you could write your own traits for that. And then your largest function would accept those traits, would accept those types because it had the correct type and it would be able to be ordered. So I'm going to call it there because we're already 2 minutes over. And one more minute? Oh, awesome. Yeah. Great. Okay. So we're going to skip right through this stuff, which is more about traits and bounded traits. So Bounded traits are quite interesting. Here we have a notify function, and it's saying that it can take a T, which is generic, but it's saying that T must implement the summary trait. So if we look at the code there, we have this item.summarize. The summarize method is part of the summary trait. So notify needs to know that whatever object it is receiving will have that summarize method. How does this relate to like the stuff we saw earlier? Well, sometimes, sometimes a function can have lots of like trait boundaries. So many, in fact, that we can go back to like terrifying subject example again. And now we know a little bit more about it, which we didn't really cover too much, so bear with me. So if we're looking at this now, we can see that it's an implementation block with the generic types T, R, P, and L. Okay, that's those T, R, P, and L are just generics. It's got an offense report system as a trait, and it's been implemented for specific types as well. Okay, it's been implemented for 2 types, option and a tuple. The for equivocation report system tells us the implementation block applies the equivocation report system that's parameterized with those generic types, the T, R, P, and L. And we can look and see what the T, R, P, and L is down in the where statement, where we'll see like things like P can be any object that implements the key owner proof system and is associated with type identification tuple, which should also be clonable, and so on and so on and so on. Okay, still not the most readable thing in the world. Hopefully, we're gonna time out. Most of us couldn't like this. I just want to put up these links for people as somewhere you can go and look into this a little bit deeper. Sorry we ran out of time with some of the technical issues there, but do we have time for questions?
Yeah, we're going to take two or
Awesome.
3 questions. So first question is, have you ever tried binding Rust code to Python using Py03?
I have not as of yet. I have to admit that because of what I currently do, my Rust is very much just Rust.
All right, second question. You've mentioned that Python and Rust packaging. Now we hear a lot about Rust integration to Python. How would you package a project that has both Python and Rust?
Again, I wouldn't, unfortunately. Everything I do these days is 100% Rust. The only thing I might be moving slightly into is that we do use Rust to build out WASM, which is what a lot of the stuff we run on, or everything we build kind of actually is executing. So I may start to look more back into Python again when WASM support becomes a little bit better.
Okay, there were a couple more questions, but we don't have any time, unfortunately, so please, big round of applause
for the rest of the day. Come say hi.